We've all been there, right? You're running a simple calculation, maybe an average on some data, and suddenly your whole analysis just stops. Well, that's exactly what we're tackling today. The super important and, yeah, often tricky task of handling missing and invalid values in NumPy. Real-world data is almost always messy, and knowing how to handle those imperfections is what really separates a script that fails from one that delivers powerful insights. So let's dive in. So here's our game plan. First, we're going to diagnose the core problem. Why do these missing values break everything? Then we'll get up close and personal with the culprits, nan and infinity, so we really get how they work. After that, we'll build up our toolkit, learning how to find them and ignore them, and then how to actually clean things up by replacing them. And we'll finish up with some advanced concepts to really make sure you've mastered this. All right, let's set the scene. You've got your data. Maybe it came from a sensor, a survey, whatever. The one thing you can pretty much guarantee is that it's not going to be perfect. There are going to be gaps, a sensor that blinked out for a second, a user who just skipped a question. These are your missing values, and believe me, they can cause some serious headaches for your calculations. Okay, let's look at a totally classic example here. We've got an array with temperature readings. Most of them look good, but you can see 2 of them are missing. Now, in the NumPy world, we represent this with a special value, np.nan. And that just stands for not a number. It's the industry standard for flagging missing numerical data, no matter if it's from a busted sensor or just a measurement that never got logged. And here it is. This is the whole problem in a nutshell. Look at the left side. If we just try to calculate the average using a standard function like np.mean, what do we get? Nan. The whole thing fails. And it would be the same story for np.max or np.sum. That's because nan is basically poisonous. Any calculation it touches also becomes nan. But, and this is the good news, look to the right. NumPy gives us a way out. It has these specialized functions, like np.nanmean, that are smart enough to just ignore the missing values and give us the correct answer based on the data we actually have. So, to really get a handle on this, we need to understand our adversaries here. What exactly are these special values, nan and inf, and what are the weird rules that make them behave the way they do? Getting this down is the foundation for everything else we're going to do. So first up, what is NaN? Well, it wasn't invented by NumPy. It actually comes from a universal computer standard called IEEE 754. It's the official technical way to represent a result that's mathematically undefined. I mean, think about it. What's 0 divided by 0? It isn't 1, it isn't 0, it's just undefined. Same thing for the square root of a negative number. Computers needed an answer for that, and the answer is NaN. In data science, we just borrow that same idea to stand in for any numerical data that's missing. Now, nan has a couple of really weird properties that you just have to burn into your brain. First, it's contagious. It's like a virus for your math. Any operation that involves a nan, the result is just another nan. But the second one, this is the real mind bender. Nan is not equal to anything, not even itself. I know, it sounds crazy, but if you type np.nan equals np.nan, you will get false. And that's exactly why we can't just use a simple equal sign to find it. We need special tools. So a question I get all the time is, hey, why can't I just use Python's none? Well, this slide is why. It's all about performance. See, np.nan is actually a special kind of floating point number. It can live happily inside a numerical array, and NumPy's super-fast machinery keeps humming along. But none? That's a totally different Python object. The second you put none into a NumPy array, the whole thing gets demoted to a generic object array. And that kills all of NumPy's performance benefits. It's like turning a race car into a golf cart. So the bottom line, for numerical data, always use np.nan. Along with nan, we've also got its cousins, inf and negative inf, for positive and negative infinity. You'll usually see these pop up for 2 reasons. One is pretty obvious, dividing a number by 0. But the other is a little more subtle. It's called numerical overflow. That's when a calculation produces a number that's just too big for the data type to hold. Just like nan, infinity is another one of these invalid values we need to know how to handle. All right, enough theory. We know the problem. We've met the culprits. Now it's time to actually build our solution. Let's get our hands on the NumPy tools we can use to find these nan and inf values and, actually get some work done. So NumPy gives us 3 main tools for this detection job. First, you've got np.isnan. Think of this as your dedicated nan detector. Then there's np.isinf, which, you guessed it, scans for any values that have flown off to infinity. And then there's my personal favorite, np.isfinite. This one does the opposite. It's like a quality check that tells you which values are good to go. The normal, finite numbers you can actually do math with. Now, the magic here is what these functions give you back. They don't give you a number, they give you a brand new array filled with just trues and falses. We call this a Boolean mask, and we can use this mask to filter our data. So let's break this code down. np.inanr gives you a mask that's true for every nan. That little squiggly line, the tilde, is a not operator, so it just flips all the trues and falses. So the whole expression is basically saying, go into my array and give me only the elements that are not a nan. It's incredibly powerful. Now, while filtering with masks is great, sometimes you just want the easy button. And luckily, NumPy has one. For a ton of common calculations like sum, mean, and max, there's a special nan-aware version. All you do is tack nan onto the front of the function name. These are just so convenient. They do all the filtering for you behind the scenes. Honestly, 90% of the time, this is going to be the quickest and cleanest way to get the job done. But what happens when just ignoring the data isn't enough? For example, a lot of machine learning algorithms will just throw an error if you try to feed them data with any missing values. In those cases, we have to go a step further. We have to move from just ignoring the data to actively cleaning it. This process has a name: imputation. It's basically making an educated guess to fill in the gaps. So, we have a few common strategies for this. The simplest is just to replace the missing values with a constant number, like 0. The function np.nan2num is perfect for that. A slightly smarter approach is to replace them with a statistic, like the mean or the median of all the other valid data points. And finally, for data where the order matters, like in a time series, you can use a more advanced method called interpolation. That's where you intelligently estimate the missing value based on the trend of the values that come right before and after it. All right, we are in the home stretch. We've covered the core ideas, so now let's touch on one more advanced topic that gives you even more power: masked arrays. We'll see how that's different from using NaN, and then we'll wrap it all up with the key takeaways you really need to remember from all this. So let me ask you a question to set this up. When is a missing value not actually gone? What if you can mark something as missing but without actually deleting the original number? Sounds a little weird, right? Well, there's a way to do it. This slide gets right to the heart of it. When you replace a value with np.nan, that original number is gone. It's a destructive change. A masked array is totally different. It's non-destructive. Think of it like putting a little piece of sticky tape over a number. The original number is still there, underneath, completely safe. You're just telling NumPy, hey, for any calculations, just pretend this one isn't here. This is way more flexible because you can always come back later and peel the tape off. The MA module in NumPy is where you find this, and np.ma.maskedInvalid is a great shortcut to get started. Okay, let's boil this all down. What do you absolutely have to remember? 1. Nans will break your standard math functions. 2. Your first move should almost always be to use the nan-aware functions. They're easy. 3. If you must replace values, you've got options, from simple constants to smarter methods like using the mean. 4. np.nan, not none, just trust me on that. And the big pitfall to avoid: be careful. Just blindly replacing all your missing data with zeros can seriously distort your results. You have to be smart about which method you choose. And that brings me to one final thought I want to leave you with. All of these tools are incredibly powerful for fixing messy data, but they also demand a lot of judgment from us. As we move from just ignoring data to actively filling in the gaps, we have to ask a really important question. At what point does our helpful data cleaning cross the line into data invention? How many blanks can we fill in before the story our data is telling is more about our assumptions than about what actually happened in the real world? It's a critical question to keep in mind to maintain the integrity of your work.